Hi, Will. I've got your questions here. Now, I think this first one we may have looked at together on Thursday before you had to leave, and I'll do it again. And it's about taking logs. Whenever you're trying to solve for an exponent, what you do is you take the logs of both sides, and the first step in doing that is to take the exponent. Take the exponent, write it in front. And then you're going to multiply by the log of the base. And then we're going to do the same thing on the other side. So x comes in front, and then we multiply by log of the base of 5. So this one's kind of an interesting question, because if we rearrange using our algebra, then I end up here with log 5 over log 3 equal to x plus 1 over x. So all I did is I divided both sides by x and by log 3. And so x and x cross out there, and log 3 and log 3 cross out there. So now you would just use a calculator, and you're going to find the log of 5 divided by the log of 3. That's about 1.5. I think it's just under that, but let's use 1.5 just so that we can work through the example and continue on here, okay? So if that's the case, then what I can do now is I can multiply this x over here, and I have x plus 1 equals 1.5 times x. And if I put all the x's on this side, it's going to be x minus 1.5x equals minus 1, because we do the opposite operation on the opposite side of the equations. So negative 0.5x is equal to negative 1, and x is equal to negative 1 divided by negative 0.5. And if you do that on your calculator, you're asking how many times does 1/2 divide into 1? And the answer is 2, which kind of seems surprising that you get a bigger answer when you're dividing, but that always happens when you're dividing by a decimal that's less than 1. And so we end up with our answer of x equals 2 there, and so that would mean that 3 to the 3 would be equal to 5 to the 2, which we know isn't quite right. That's 27 equals 25, right? I just put 2 in for x in each case there. That's because we rounded the 1.5, and it was really like 1.46 or something like that, okay? And so if we use that exact value, the 1.46, and kept a lot more decimal places, we'd get a lot closer to the actual x value. And the idea would be that when we're trying to put it back in the equation, that the left-hand side equals the right-hand side. Okay, so here's the second question, and this is a horizontal asymptote question, and we talked briefly about those, and then I made you a video. So there's kind of a technical way to do these, and then there's sort of a shortcut way to do these. The technical way to do these is to take the highest exponent of the variable that you see in the equation. So in this case, x squared is the highest. And what you do is you rewrite the equation with all of these guys being divided by that, like this. See, so everybody's being divided by an x squared, okay? Now, if we do that, then anything that has a smaller degree in the numerator, when I let this go to infinity, anything like that, like this one for instance, is going to go to 0, because you're dividing by a much bigger number on the bottom than you have on the top. So this one's going to go to 0, and 1 is already insignificant. If you already have $1 million, you don't need one more dollar, right? And so by the time that you simplify this, then you end up just with 3 over 2 left over, because the x squareds cross out here. And so that is your HA, your horizontal asymptote. The quick sort of shortcut way to do this is sort of to look at the equation overall, go back up to the top here, and just ask yourself, you know, if I have infinity squared, is infinity even important? And the answer is no. And so you just kind of like ignore all of the terms other than the highest variable, or the highest degree of the variable, and then you just simplify that. And so obviously x squared divided by x squared gives us 3/2, the same way that we got it doing it the technical way. And so that's how you find the horizontal asymptote. And then again, you would do your test to see how the curve is going to behave as it comes close to that asymptote. And the test this time is going to be using the original equation minus the value of the asymptote, and you're going to substitute in large X, small x, so in other words x equals 10, x equals minus 10, and see whether it comes out positive and negative. And remember, positive is above the asymptote and negative means below, and so that helps you graph the curve using the asymptote. All right, so the last question that you asked about was this one, and this is an interesting one because they want to know what value of k will make this a continuous function. And so what they mean by that is that they can't have a break in the graph. And because it looks like something different is happening around the value of x equals 2, because the function is defined as one thing for x values less than or equal to 2, and then as a different function when x is greater than 2, then we need to make sure that when we're graphing it, if we're coming along with one function and we stop at x equals 2, then we start up with another function that if it's going to be continuous, there can't be any gap in the graph at x equals 2. So in other words, the y value has to be the same, or the function has to have the same value for both of these equations at x equals 2. And so all they're really asking you to do is just say that at x equals 2, kx squared would have to be equal to x plus k. And we know that's just at x equals 2. And so we're going to fill in the 2 for x. So we have 4k equals 2 plus k. And if I rearrange this equation, I'm going to bring k over to this side and subtract it and have 2 on the right. So I have 3k equals 2 and k equals 2/3. And so if the k value is 2/3, in other words, the function then would be 2/3 x squared if x is less than or equal to 2, and x plus 2/3 if x is greater than 2. Then the function will be continuous because right at 2 we'll have the same y value for both functions. So wherever it leaves off on this function, it's going to pick right up again at x equals 2 at the same y value for the second function.